Hello everyone, my name is Andrew Kim and welcome to the third video of my AP Physics C review session. Now in this video, I'm going to talk about the second part of the circuits, which would be about capacitors and inductors. So let's get started. Okay, so circuit part 2. I assume that this video will be shorter than the other ones because it's basically the second part. And also, it's only going to cover two things, which are capacitor and inductors. And technically, in my RLC circuit video, I also do talk about capacitors and inductors. So I'm going to keep it short. But anyways, let's get started. So capacitor. Think of capacitor as a portable charger. It literally stores the charge. Now, of course, when you have a capacitor, the capacity of, we have to talk about the capacitance of the capacitor or the capacity of the capacitor. Basically what it is it tells you how much charge, how good your capacitor is in actually storing the charge. And this capacitance is expressed with the alphabet C, and that can be calculated under the formula of this, epsilon 0 times kappa times A over D. Now, epsilon 0 is a constant. It's going to be given in your formula sheet, so you don't have to worry about it. Now, A is the area of the plates that you have. Now, for example, so capacitor looks like this on a circuit. This is the symbol of capacitor. And there's a reason why the symbol looks like this. It's because basically capacitor literally looks like this. You have two plates side by side, and in those plates, you want to charge negative charges. You want to store negative charge in one side and positive charge on the other. So of course, if the plate is larger, you would be able to store more negative charges and positive charges. That is why you have A on the numerator, so that when the area increases, the capacitance also increases. Now, D is the distance between the two plates. And think about it. If the distance between the two plates is more farther away, it basically means that the force between the attracting force between the negative charges and the positive charges would be lower. Thus, there will be less negative and positive charges stored in each plate. Thus, D is in the denominator, so that when the distance between the two plates increase, then the capacitance decrease, and when the distance between the two plates, in fact, decrease, then the capacitance increase. So that's why you have A and D. Now, then what is kappa? Well, in a lot of questions, kappa might not be required. You would be just simply able to calculate C under the formula of epsilon 0 times A over D. However, there are some questions, and those questions are the ones where you have a cheese block or a certain block in the middle of your capacitor. And for those questions, what you have to do is multiply kappa, or the constant of that block in the middle of your plates. Why? Well, basically, when you have a certain block in the middle of your plates, and when you have nothing, when it's vacant, or when there's only air, of course, it's going to be different. Of course, the amount of charge that can be stored between the two plates are going to be different. If you have something blocking, if you have an object between the two plates, then of course you would have less charge that can be stored. Well, it's not. In fact, if you have something in between of the two plates, then actually you can store more charge, because normally you don't just put some random cheese block in between of your two plates, but you actually put in some specific metal that actually helps the charges to be gathered in the two plates. So most of the times, if you have an additional metal piece in the middle, then kappa would be greater than 1 and thus increase your capacitance. But anyways, that's how you calculate capacitance. Now, as you can see, capacitance is a physical trait, just like resistance of a resistor. Capacitance is a physical trait. It does not change depending on how much current is flowing or how much voltage is across your slide, but it is a unique and independent characteristic. It is the characteristic that the capacitor itself has. Thus, now we're going to talk about Q equals to CV formula. Even in this formula, no matter Q changes or V changes, your C cannot change. Your C can only change when your physical traits of your capacitor change. For example, if the plates on your capacitor increase, or the distance between your two capacitor plates change, or something like that, that's the only case when the capacitance can actually change. Now, that being said, let's look at this formula Q equals to CV. Q equals to CV. Q is the charge that can be stored on your capacitor, and V is the voltage across your capacitor. Now, what this formula is telling you is that the charge that can be stored on your capacitor is equal to the capacitance, the ability of your capacitor to store charge, times voltage across your capacitor. Now, this makes sense because, of course, if you have higher capacitance, that basically means that your capacitor's ability to store charge is greater. Thus, you would be able to store more charge. And of course, if voltage is higher, it basically means that the potential energy across the two plates are greater, or the downhill. If you've watched my previous video, you would understand this downfall, this water flow analogy. Now, if you have greater voltage, it basically means that your downfall is greater. The height difference from the highest part and the lowest part of your slide is greater, meaning that more water would flow more rigorously. Thus, of course, there will be more charge stored on your capacitor. Your capacitor would work better because you have a better working slide. So that's basically it about the Q equals to CV formula. Now, Q equals to CV formula, you would use this formula so much because some question literally asks you how much charge is stored in this capacitor C1. And then you would have to calculate it by using the physical traits of C, or C capacitance might be given from the problem, and multiply that to the voltage difference across your capacitor. Now, the next thing that you have to know is this formula, E equals to 1/2 CV squared. And now what this formula is telling you is that this formula tells you how much energy, this time not charge, but energy that's stored in your capacitor. Of course, as I said, capacitor is like a portable charger. If there's a charge that's stored on your portable charger, of course, your portable charger would also have energy stored on it, right? Now, this energy stored on your capacitor can be calculated under this formula, 1/2 CV squared. Now, this formula might look kind of tricky because you have 1/2, you have a coefficient, and you have you have 2, which is an exponent. However, think about it this way. What was the kinetic energy? How do you calculate this? 1/2 mv squared. What is the elastic potential energy? Well, that was 1/2 kx squared. This 1/2 something something squared is a very classic structure that occurs often in energy in physics. So same, 1/2 CV squared. Let's remember this formula because some question might literally ask you what's the energy stored in your capacitor. Now, when a question asks what's the energy stored in your capacitor, it's asking the energy, not the charge. So please don't get confused. Now, finally, let's talk about adding capacitors. Now, capacitors can be added in two ways, just like resistors, parallel and series. Now, the thing is, if we add the two capacitors in parallel, what's going to happen is that in both capacitor, they would first of all have the same voltage difference across it. Why? Well, you would already know this if you watched my previous video, if you understood the water flow analogy. The water flow left to the capacitor and your water path right to the capacitor have different height. However, your water flow, the height before both of the capacitor and after both of the capacitors are literally the same. Now, I'm not saying that before and after is the same. I'm just saying the height at each capacitor before is the same, and the height at each capacitor after the capacitor is the same, meaning that the height difference across the two capacitors should be the same. Thus, the voltage difference across the two capacitors should be the same because you're starting at the same point and you're ending at the same point. Thus, you would have to fall the same height. Now, one interesting thing is that if the capacitance of each capacitors were C1 and C2, then you can in fact combine the two capacitors, and the resulting capacitance would be the sum of the original two capacitors, thus C1 plus C2. Now, this wasn't the case for resistors. For resistors, you needed to use this formula when the resistors were connected in parallel. However, in capacitors, when they're connected in parallel, you can simply just add up the original capacitance in order to calculate the final capacitance. Now, also, what you can do is you can combine two capacitors in series. Now, what's going to happen in this case is that, let's say over here, you have plus Q stored. Now, if you have plus Q stored in your left plate of the left capacitor, on the right plate of your left capacitor would have minus Q stored, because the two plates are basically looking each other. They're basically corresponding together. One plate is inducing the charge in other plate. So of course they should have the same charge, but opposite sign. Now, if you have minus charge on this plate that I just colored in black, the plate over here that I just colored in blue should have plus Q charge. Why? Because this part is in fact connected in one wire. Thus, the sum of their charge should be 0. If you have negative Q charge on one side, then in the other side, you should have plus Q in order to cancel it out. Because this part of the wire, this fragment of wire is not, it can't just be negative Q charge as a whole. As a whole, it should have 0 charge because it's a wire, it's a neutral wire. Thus, this right side should have plus Q charge. And if this right plate have left plate of the right capacitor has plus Q charge, then this red part or the right plate of the right capacitor should have negative Q charge, because again, one plate induces the charge and the other plate, they correspond. They should have the same charge but opposite sign. Thus, you will have negative Q. Now, what you can see is that in both capacitor, you have Q amount of charge stored. You have same amount of charge stored in both capacitors. That's our conclusion. When you connect capacitors in series, then you have the same amount of charge stored in both capacitors. And of course, you can combine the two capacitors into one singular capacitor. And the resulting capacitance, if you use C for that, then you can use the formula C1 over C equals to 1 over C1 plus 1 over C2 to calculate this combined capacitance. Similar to, or this literally the same as what you do for the resistance when the resistors are connected in parallel. So basically, how you calculate the combined capacitance is literally the opposite as how you calculate the combined resistance. So you use resistance method when it's parallel for capacitor method when it's in series. And you use the resistor method in series when you connect capacitors in parallel. So that's how you would do things. I'm so tired, guys. I honestly want to just stop this video, but I'm going to continue. The next thing we have to learn is inductors and solenoid. They're the same thing. They look like this. Looks like a coil. And you literally use this symbol in your circuit. And of course, similar to capacitance and similar to resistance, inductors also have something called inductance. And you use the symbol L to denote that. Now, L is equal to n squared times mu times a over L. Now, whenever you see a Greek alphabet, epsilon, kappa, mu, with a very high probability, that's going to be a constant. And indeed, the mu over here is a constant. It's going to be given from the problem. Now, A is the area, of your coil. Now, when I say area, it's this vertical area. It's the cross-section area of your solenoid. Now, what this formula is telling you is that if the cross-section is wider, if the area of your cross-section is greater, then basically the inductance is greater. Now, there isn't a good way to actually explain this and make this sense, make this make sense. For capacitance, I was able to explain why each variable is in either denominator or numerator, but for inductor, sorry, I can't really explain why A actually affects it positively, or proportionally. Sorry for that. But anyways, you have A, or the cross-section area, on your numerator. Now, another thing is N. Now, N stands for number, or the number of times this coil is wrapped. So if the coil wraps just once, then N will be 1. If the coil wraps twice, then N will be 2. If the coil wraps 100 times, then N will be 100. Now that goes on your numerator, which makes sense because if the coil is wrapped more, then of course the inductance, how good the inductor is, will be higher because inductor is literally a coil. And what makes a coil a better coil? When the coil is more wrapped around, right? So that's why N is on the numerator, and N is so special that it has power of 2 or square. Now on the denominator, you have L, or the length. Now that's kind of weird. I mean, L is the length of the inductor, and if the inductor is longer, it might sound like that the inductance should also be greater, because in the case of resistance, when the resistor was longer, then the resistance was also greater because it's longer. But in the case of inductor, that's not how it works. Simply because if it's longer, then basically what it's telling you is that if it's longer, but your N still stays the same, it means that the inductor got longer, but still you wrap the same number of times, meaning that how densely wrapped your coil is decreased. And thus, since it's not densely wrapped enough, the identity as a coil, the identity as an inductor should have decreased. Thus, inductor decreases, inductance decreases. That's why L, the length, and L, the inductance, are inversely proportional. And that's why L, the length, goes to the denominator. Yay! Now the thing is, oh my gosh, I forgot to even explain how inductors are used. Sorry, I'm losing my mind. It's 1:50. It's the 3rd or 2nd day of spring break, and the only thing I've done during the spring break is making videos. My mind is popping out. Anyways, I forgot to explain what inductors are after all. Inductors are basically, it's like a coil, and how it works is that if current goes through it, then it induces a magnetic field through the middle of it, like this. So that's how inductors work. Now, if you ask me what's its significance in real life, I mean, like capacitors had its significance, like stored charge, and resistor had its significance, reduce the current or reduce the voltage. But what is the real life significance of an inductor? Well, you can use that for electromagnetics, which I'm going to explain in the future video, in order to create magnetic field. That's it. It doesn't really have any significance within the circuit, but it's going to make some magnetic field, which is pretty significant. Now, of course, you have similar to the capacitor, for inductors, you can also calculate the energy stored. Well, it's not really energy stored, but it's like the energy that the inductor has or the inductor is going through. And that can be calculated as a U, which stands for the energy, equals to 1/2 Li squared. Again, this 1/2 mv squared, 1/2 kx squared, this 1/2 something something squared formula maintains for this situation as well. 1/2 Li squared. I is, of course, the current that's flowing through the solenoid. Now the last thing, what happens if you add inductors? Well, of course you can add in two different ways. Of course, that was the case for both the resistors and the capacitors. Now, if you add the two in parallel, as I'm repeating over and over, of course they would have the same voltage difference, because if you consider them as a slide, they start from the same point, end at the same point, meaning that they drop the same amount of distance. Thus, they should have the same voltage difference. Now, if you have L1 as the inductance of the first inductor and L2 as the inductor of the second inductance, then of course you can combine this just like how you've done with resistors and capacitors, but the resulting L, or the resulting inductance, can be calculated under the formula of 1 over L equals to 1 over L1 plus 1 over L2. Now you can notice how this is the same as resistors. Yes, resistors and inductors have the same way to combine them, and capacitance has the exact opposite way to combine them. Meaning that if you combine L1 and L2 in series, that will be equal to a singular inductor with the inductance L, which is equal to L1 plus L2. Yay! Again, it's the same as how you do with resistors. Now, you can notice how for inductors, I explained significantly shorter amount of time, probably like 5 minutes, whereas for resistors, I explained more than 10 minutes. There's a reason for it. Sorry, capacitors, I explained more than 10 minutes. Now, there's a reason for that. Inductors are harder. So the AP questions are going to ask less. And even for the questions that the questions actually ask, they're going to ask to a shallower degree. They're not going to go deep into. They're just going to simply ask like this, you have this coil, it's wrapped this number of times, its sectional cross-section is this, what will be the inductance? Something like that. Something very simple. So you won't really have to worry about this. Honestly speaking, all these things might not even really appear. I remember using this formula, this inductance formula, a lot of times for unit tests, for whatever. So I would say this is something that you would have to keep in mind. But apart from that, honestly, you won't really see the other things in inductors unless you talk about LC circuits in the future. And if you want to know more about LC circuits, you can watch my video, my 7th video, I believe. So that's it. Now we finished circuits as well. Circuit number 1, the first part of the circuit, the second part of the circuit. Now in my next lesson, I'm going to talk about magnetic field. That's a whole different topic because we've talked about electric field and then about circuits. Now it's our time to talk about magnetic field. I believe magnetic field isn't really harder than the other two, so you won't really have to worry. Yeah, that's it. Thank you for watching my video as always, and please don't forget to have a great day.